Okay, let me make this full screen. All right. So welcome to the Introduction to Deep Learning talk. So my name's Andy Beam. I'm an assistant professor at the Harvard School of Public Health. I'm based in the Department of Epidemiology, but my training is in statistics and computer science. My group does deep learning research for medical applications. We have a special focus on neonatal and perinatal medicine, but we do lots of sort of medical deep learning projects pretty broadly. So I'm going to be a lecturer for you today and tomorrow. Today's lecture is primarily going to be conceptual. So what I hope to do is get you excited about all the cool stuff that deep learning can do, give you a little mental model for what I mean when I say deep learning, before I make you do a little bit of math tomorrow. Tomorrow is going to be a more technical talk where we go through some of the nuts and bolts about how a neural network works. But today is going to sort of be pure unrefined sugar, and we're just going to have fun talking about all the cool stuff that people are doing in deep learning and artificial intelligence. The other thing is I would love if you all have questions, if you ask them. I think putting them in chat, I can see when there's a question in chat. I think it probably makes sense we can unmute people, Amanda, and let them ask their questions on camera. But it'd be much better than having me talk at you for an hour, that you all ask questions as we go through. So since this is the first lecture, I'm going to give you first just a little background on machine learning, which is sort of the discipline in which deep learning traditionally operates. So what do we mean by machine learning? So it goes back to 1956. This guy that I'm showing you named Arthur Samuelson was the first person to coin the term machine learning. And broadly speaking, it means the field of study that gives the computers the ability to learn without being explicitly programmed. So Arthur's example where he introduced this term was creating a system that could play checkers. And you can see Arthur interacting with his machine learning checker system here in this picture. And the interesting thing about this, and one of the things that we'll revisit a couple times, is that machine learning gives you the ability to create programs that can do things that you don't know how to do yourself very well. So Arthur, by his own admission, was a terrible checkers player, but he was able to create a machine learning checkers playing system that could routinely beat him and beat very good checkers players. And so that is, I think, one of the sort of magical things about machine learning is it gives us the ability to create programs that can do things that we ourselves don't know how to do. When you read the machine learning literature, depending on sort of what applications you're talking about, it can look an awful lot like statistics. So we will talk about some machine learning applications that look like regression, that look like classification. And then we're going to talk about some applications that look nothing like statistics. And so sort of depending on the area or the project that you're working on, it can look a lot like related disciplines like computer science, mathematics, and statistics. But sort of the overarching goal, I think, is the one that Arthur put out here in the 50s, which is we want computers to learn how to do things by themselves without us explicitly having to tell them how to do it. So if you take a machine learning class, you're going to see something that looks like this. I'm going to tell you a little bit about how this trichotomy is a little bit dated now. But machine learning has historically been divided into three different tasks. Supervised learning, this is the sort of area where it's going to look a lot like a stats model if you've taken a statistics class. But supervised learning is where we have an outcome that we want to predict. In machine learning jargon, this is going to be called a label. But basically, we have inputs and we want to predict new outputs using an algorithm or a model. Then we're going to have unsupervised learning, and this is where we have a lot of data, but we may or may not have an outcome or a label for that data, and we'd like to be able to either partition our data into homogeneous subgroups, often called clustering, or do something else like that when we don't have the benefits of labels or outcomes. And then the third paradigm is traditional reinforcement learning. And this is going to be the most distinct kind of machine learning. And it's where we think about we have something called an agent, and we want the agent to move and behave in some type of environment or world in an intelligent way. And so the example that I'll cover is, can we make an agent play a video game at a very high level? So can we train sort of a model to play a video game or chess or other types of games at a very high level? But the big difference here is there's a notion of time. So the agent has to be able to make smart decisions as the game progresses. And it's trying to maximize this specific quantity called reward. So I'll dive a little bit into each one of these over the next 5 minutes or so, just to give you a little background on where the deep learning stuff that we're going to talk about fits into the larger machine learning landscape. So another way to think about these three different categories is the kind of data that you have. So almost always when you're going to go through your machine learning, deep learning, and statistics journey, you're going to see something called X. And X are the inputs to your model. So X is sort of the data that you have, and Y here is the outcome or the thing that you want to predict. And so when we're talking about supervised machine learning, we have both X's and Y's. So we have both inputs and outputs, and we'd like to predict new Y's using new X's. And so if you've taken a stats class, these will look like regression models, like classification models, but basically what we're trying to do is make predictions. We've collected a lot of historical data where we have the X's and we have the Y's, and we're anticipating getting new X's in the future, and we'd like to sort of automatically predict the Y's that go with those X's. Unsupervised learning then is where we don't have Y's. We don't have those prediction targets, but we would still like to infer interesting properties of X. So I mentioned clustering or dividing our X's into homogeneous subgroups. That's sort of the canonical example for clustering. And then reinforcement learning is we still have X's, but now we have this new thing called R, which is the reward that we want our agent to maximize. So in the video game example, you can think we want our agent to get a high score, and the high score here would be the reward or the R that it's trying to maximize. So let me quickly give you an example of supervised learning. So I will say just upfront, 95 to 98% of what gets talked about in machine learning and what people call artificial intelligence is actually just supervised learning. And again, that's just where we have these X's and we want to predict Y's. If we want to make this precise in statistical language, it comes down to estimating some conditional distribution. So we want to know what is the probability distribution of Y given X. If Y is discrete, meaning that it's a yes or no, or it's a bunch of different categories, then we would call this classification. If Y is continuous, then it's going to be regression. So if we're trying to predict some real valued outcome, like you predicting height on the basis of mom and dad's height or something like that, then that's going to be regression. And there are lots of popular methods historically to take on this. And so we're not going to go sort of through the entire catalog of supervised machine learning. We're going to focus specifically on one approach that's been very popular over the last 10 years called neural networks. So let me give you a pictorial example of how supervised machine learning. So I work in medical applications. And let's say that I would like to kind of create an AI ophthalmologist. So I would like to be able to diagnose a condition known as diabetic retinopathy using pictures of people's eyes. And so the way an ophthalmologist would do this is they would take what I'm showing you here, which is called a retinal fundus photograph, which is just a picture of someone's eye. They would look at that, and on the basis of this picture would say this person either has the condition or they don't have the condition. So how would we train a supervised machine learning algorithm to do that? Well, we would take our picture, we would show it to our machine learning algorithm, and tomorrow's lecture will be opening up this black box and explaining sort of the mechanics of what's going on inside that. But just for now, follow along conceptually. And what this algorithm is going to do is make a prediction. So in this case, I'm just asking it to tell me whether or not this picture is a picture of a healthy eye or a sick eye. So it's going to make a prediction, and I'm going to give it the correct answer. So in this case, this is a picture of a healthy eye. So let's imagine that it had guessed, okay, this is a sick eye, and it's going to give me the probability that this is a picture of a sick eye. What the algorithm is going to do is look at the discrepancy between the ground truth label that I gave it here, the Y value, and its prediction, and use that to go back and update its internal parameters so that the next time it sees this picture, it's more likely to guess the correct answer. So likewise, I'm also going to show the algorithm pictures of sick eyes. And so again, it's going to do this kind of guess and check procedure where I first show it the picture, it guesses whether or not that's a healthy or sick eye, then I give it the correct answer. In this case, this person does have diabetic retinopathy, and it's going to use the discrepancy between its prediction and the ground truth label to then go through and update all of its parameters. And we could stop the lecture here because this is essentially how supervised machine learning works. And this is what people refer to as training the algorithm. So when you train an algorithm to solve some prediction task, you're really just feeding in a bunch of labeled examples where you have inputs. You have over here on the left, sometimes you'll see them called features. These are the X's that I was talking about earlier. to predict these outcomes, or you'll also see people call them labels, or the whys. And the algorithm is just going to do this guess and check procedure in some instances, millions of times, until it learns to recognize the thing that we want it to recognize. So again, going back to a couple slides ago, I'm not an ophthalmologist. I don't know how to diagnose this condition. I really couldn't tell you much about what's going on in these pictures. I mean, I can obviously look at this one and say something doesn't look great there because there are all these spots and blotches. But I actually don't know the sort of disease signature of diabetic retinopathy. But I can, using this setup, create an algorithm that can recognize diabetic retinopathy just by showing it these labeled training data points. This is a little bit of a double-edged sword because I don't have a lot of control over what parts of the image the algorithm's actually using to make these predictions. So if there's something in here that is sort of correlated with the outcome, but it actually isn't related to the disease pathology, it's going to use that information. And so sort of a consequence of that too is it doesn't actually tell me how it's making a decision. So an ophthalmologist could look at this and say, oh, well, the vasculature here is splotchy and there's some ruptured blood vessels and the optic disc is cloudy or something like that. But the algorithm is not going to do that. It's just going to spit out a probability that this eye is healthy or sick. So we sort of have to be comfortable with that fact when we use complicated machine learning algorithms.